Actually, I think I will go through all the steps with you just so you have a chance to see it again. So here I have a population of 4 people. I mean, a population of 5 people. I've recorded 5 data values from them. So maybe I've recorded the number of I'm not sure what these numbers would stand for, but maybe it's the age of each person. So maybe I've recorded the values of 4 of these 5. Maybe I've recorded the ages of these 5 people, and these people are between 10 and 18 years old. Now I'm going to calculate the standard deviation of their 5 ages. So I found out that the mean age is 14. So I need to subtract all 4 values by 14. That's the first step. When I subtract each value by the mean, I get deviations. So 10 minus 14 is -1. I'm sorry, -4. So remember, this -4 is just saying that this person's age is 4 below the mean of 14. 12 minus 14 is -2, because remember, this person is 2 below the mean, so they have a deviation of -2. This is 0, +2, and +4. I've just subtracted each data value by the mean. Now, after subtracting each value by the mean to get deviations, well, before we've been doing a column of absolute deviations, but if I'm not planning on calculating the MAD, I actually don't have to get the absolute deviations. I can just skip to the squared deviations. The whole point of doing the absolute deviations is to be able to get the average of those absolute deviations, which is what the MAD is. But if I'm not interested in getting the MAD, I don't have to get the absolute deviations. So I have to square each deviation. So I'm skipping to the squared deviation column. -4 times -4 is 16. -2 times -2 is 4. 0 times 0 is 0. 2 times 2 is 4. And 4 times 4 is 16. Remember, the next step is adding the squared deviations. These add up to 40. And if it's a population, you divide by the number of squared deviations, which is 1, 2, 3, 4, 5. This number that we're dividing by is called n. It's the number of squared deviations, and it's also the number of people, because remember how each person has his or her own squared deviations. So if you have 5 people, you have 5 squared deviations. So it's really just the sample size. And when you divide by n, it comes out to 8. So when I divided the total of the squared deviations by n, I got 8, which is my variance. It's the variance of this population of 5 people. The standard deviation would be the square root of the variance. It's about 2.8. as a standard deviation. And I didn't show you the very first step when I got the mean of the data, but to get the mean of the ages, I just added the 5 ages and divided the total by 5, and I got the mean of 14. Then I went ahead and subtracted each age by the mean of 14 to get these deviations. I squared the deviations. I multiplied each deviation by itself. Then I added the squared deviations to get a total of 40. Then I divided that total by the number of squared deviations, which is 5. There's 5 of them, and I got the variance of 8. Then the square root of the variance became my standard deviation. That's how you do it when you have data from an entire population. Now, what if the data had come from a sample of 5 people? Meaning, what if instead of an entire population of 5 people, it was just a sample of 5 people that were recruited from a bigger population? Well, in that case, there would be one step that would be a little bit different. Everything up to here is the same, would be the same. So every step that I did up until I got this total of 40 would be the same with the sample. Where the difference would come in is the dividing step right here. Instead of dividing by n, which is 5, I divide by 1 less than n. So if there's 5 people, if there's 5 squared deviations, 1, 2, 3, 4, 5, like they are here, instead of dividing by 5, I divide by 1 less than 5. And this number is called n minus 1. So if n is 5, like it is here, n minus 1 is 4. If I had 7 squared deviations in this column, n would be 7, and I would divide by 6, because n minus 1 would be 6. If I had 10 squared deviations in this column, n would be 10, and n minus 1 would be 9, so I would divide by 9. So if it's a sample, I take the number of squared deviations, and I drop it down by 1, like I did here, and I divide by that number. So instead of dividing by 5, I'm dividing by 4. And when I divide, it comes out to 10. That's the variance of my sample. Once I get the variance, the standard deviation is the same step that it always is. I just take the square root of the variance. So it's going to be the square root of 10. Which comes out to 3.16. So what this adjustment has done by dividing by 4 instead of 5 is that it's increased the variance and the standard deviation. Over here, when I divided by 5, the variance was 8. But here, when I divide by 4, it comes out to 10. So it went up. Here, the standard deviation came out to, about 2.8. But when I divided by 4, it came out to 3.16. So when I divide by 4, like I did here, the variance went up from 8 to 10, and the standard deviation went up from 2.8 to 3.16. So both of the values increased. And but remember that the value that we really care about is the standard deviation, because that's what's commonly used to measure dispersion. So I wanted to talk about the reason for this n-1 adjustment. The reason why is because when a person collects data from a sample and the person calculates the mean and the standard deviation of the sample, what the person is trying to do is use the mean of the sample. Well, use the mean of a sample to estimate the mean of the population, to get a rough idea of what it equals, and to use the standard deviation of the sample to estimate the standard deviation of the population. So when a person collects data from a sample, the person will typically calculate the mean and the standard deviation of the sample, and what those two values are meant to estimate what the values would have equaled if the person did have data from the entire population. So I'll give you an example. Imagine that I record the heights of 100 JFK students. That's my sample. And then I take those 100 heights and I calculate the mean and the standard deviation of my data set. What I'm probably trying to do is I want to use the mean of my sample to estimate the mean height of all JFK students. In other words, I want to use the mean of my sample to estimate what the mean equals across the entire university. And what I also want to do is use the standard deviation of my sample to estimate the standard deviation of the entire university. In other words, I want to use the standard deviation to estimate the amount of dispersion across the entire university. So I want to use my sample mean to estimate the mean of the entire JFK population, and use my standard deviation to estimate the standard deviation of the entire JFK population. Now, my sample, if I used a decent sample size, my sample mean should do a good job of estimating the population mean. But the standard deviation of my sample will only be expected, I can only expect it to do a good job of estimating the population standard deviation if this adjustment has been used. If I didn't use this adjustment, n-1, and I just calculated my sample standard deviation by dividing by 5, then what would happen is it would be likely that my sample standard deviation would come out too low, and it would underestimate the standard deviation of the JFK population. So what this adjustment is meant to do is to boost the sample standard deviation up to a bigger number so that it's less likely to underestimate the population standard deviation.